All right, welcome back. I hope you're having an awesome time so far. Our next speaker is Marta Batlle. She is a data scientist at Roche. Please join me in welcoming Marta to our virtual stage.
Hi, thank you, Patricia. Let me share my screen here. Okay, good. So thank you for the introduction and thank you all for being here today. I am very excited to be here to quickly walk through how we are leveraging generative adversarial networks in healthcare. And so I would like to start by giving you a bit of an introduction to what are generative adversarial networks, or GANs. And to do so, I'd like to start with a little game. Can you all look at these two pictures and think, or even write in the chat, which one do you think is a real person and which one is not? Do you all have your answers? Both images are fake. Actually, none of these people exist in the real world. They are generated with a type of deep learning model called Generative Adversarial Networks, or GANs, which allow us to generate really realistic data, just like you can see here. So GANs were proposed by Ian Goodfellow and colleagues in 2014 and have improved really fast since. A GAN is composed by two neural networks that are trained simultaneously. A generator that is able to generate new samples, and a discriminator, which is able to tell whether a data instance is real or fake. A common analogy which I love is the one of the art forger and the art inspector. In this example, we have an art forger, the generator, which tries to forge paintings, and an art inspector, the discriminator, which tries to detect imitations of paintings. The art forger and the art inspector are constantly trying to outsmart each other, because the better the art forger or the generator is at generating imitations of paintings, the better the art inspector or the discriminator needs to be at distinguishing between real paintings and imitations. So let's dive a little bit on the more formal definition of GANs. A GAN is trained by an adversarial process in which we simultaneously train two neural networks. A generative model that can generate new data instances by looking at the data distribution, and a discriminative model that estimates the probability that a sample is real or not, and is therefore able to discriminate between real or synthetic data. More formally, given a set of data instances X and a set of labels Y, a generative model captures the joint probability X and Y by modeling the data distribution, which basically tells you how likely a given example is. On the other hand, the discriminative model captures the conditional probability Y given X by drawing a line in the data space. This tells you the probability that a label applies to an instance, or in other words, that a handwritten 0 is actually a 0. When both networks are trained simultaneously, both get better at doing their jobs. This learning can happen through backpropagation. The loss derived from the output of the discriminator is sent back to the generator, which uses this feedback to update its weights. GANs can be used for a myriad of applications. Let's look into the coolest ones. AI, and in particular GANs, have changed the world of image editing and manipulation. One of the biggest breakthroughs was Photoshop 22.0, which now comes with a new addition called neural filters, which are trained with GANs. Neural filters allow users for deeper edits, such as changing the subject's age or facial expression, amplifying or reducing feelings of joy or anger, and removing specific features such as the glasses. Of course, many editing programs and social media platforms now come with these features. In the field of image processing and editing, GANs have also proved to be really good at improving the resolution of images, as well as image restoration and reconstruction. Style transfer was definitely a breakthrough in the evolution of GANs. Image style transfer allows us to apply the style of one image onto another image, while keeping the output really realistic, just like you can see here. For example, we can transform a zebra into a horse, or we can generate paintings with the style of different famous artists. For example, you could paint the Golden Bridge with the style of Edvard Munch, the artist who painted the Scream. As you can imagine, style transfer is widely used for image filters in social media platforms. Another interesting application of GANs is text-to-image translation. This allows us to generate realistic images based on text. These models have the added complexity of having to match words to images, but as you can see here, they still do a pretty good job at it. This application can be really useful for designers or marketing specialists in order to get inspiration from the variety of outputs of GANs, or to generate quick designs from sketches. Significant attention has been given to GANs from all different industries, including healthcare, finance, arts, manufacturing, etc. This led to the development of many GAN architectures, and that have driven a huge increase in the performance of GANs over time. GANs have also been adapted so they can now take many types of data, such as tabular data, text data, audio, video, and electronic health records. In the field of image processing, GANs have also achieved great success when applied to medical images. Image generation and segmentation are some of the key applications of GANs in healthcare. Having a sufficient amount of high-quality data is crucial for building high-performance algorithms that can help researchers unravel the underlying mechanisms of disease and prognosis. However, medical image acquisition and annotation is an incredibly timely and costly process that makes it very difficult for researchers to acquire sufficient label training datasets to train their machine learning models. GANs can therefore provide a powerful solution to the lack of data in medical imaging. For example, here we can see synthetic images of human embryo cells that could be obtained during cell development processes. These synthetic images were later used to facilitate the development, training, and validation of ML models for cell development. GANs can also provide a solution to the challenges of medical image segmentation. Image segmentation is used to identify regions of interest in a medical image, such as the precise structural details of different organs or tissues, or to identify tumors. For example, image segmentation can help researchers and doctors assess tumor growth and evaluate brain atrophy, which is a common biomarker of the progression of Alzheimer's disease. Here, you can see that CycleGAN achieved a similar performance to the expert's performance in segmenting the kidney. In current clinical practice, multiple imaging modalities are available for disease diagnosis and clinical assessment. Some imaging modalities might be more popular than others for certain patient populations, and these, added to the many difficulties in collecting medical images, emphasizes the need for researchers to develop methods that allow us to transform images from one modality to another. In this example, in the same way that style transfer allowed us to transform zebras to horses, researchers were able to transform MRI images to CT images with great quality. This facilitates availability of data from different modalities and benefits segmentation tasks. While most applications of GANs in healthcare have been developed in the field of medical imaging, there has been an increasing focus in generating discrete medical data. Most efforts are focused in using GANs for augmenting tabular datasets, such as with conditional GAN for tabular data, and also for generating synthetic datasets for privacy. GANs have brought also high expectations in the analysis of electronic health records, including not only multi-label discrete records, but also unstructured text, providing a step forward in the field of natural language processing. So now you might be wondering, how are we leveraging GANs at Roche? At Roche, we were aware of the great potential of GANs in healthcare, so we started to investigate how GANs could help us solve two of the most important and pressing challenges in the healthcare analytics domain: data augmentation and data privacy. Modern machine learning models, such as deep neural networks, may have billions of parameters and require massive labeled training datasets, which are often not available. Healthcare data is really difficult to obtain, either because it is very expensive, such as with medical images. There are no easily accessible tools to gather this data, such as with medical gadgets, or because of privacy concerns. GANs could be a solution to exploit the power of the very valuable data that we already have available. With GANs, we can augment the size of our datasets while also adding variation to our data, which will lead to better and more generalizable ML models. AI trends are moving towards a data-centric approach, in which the protagonists are not models anymore. As ML scientists, if we want to build models with high performance, and that means not only high quality results, but also outputs that are generalizable, we need more and better data, and we need to put more focus on understanding the underlying data distributions. Most healthcare datasets have unequal class distributions, which can be due to the data collection process. The performance of ML models is severely hindered when trained on imbalanced datasets, since the model is not exposed to sufficient samples of the minority class during training, and therefore shows poor testing performance. While resampling techniques are popular when tackling these problems, they are not as useful as other techniques. At Roche, we're exploring how to leverage GANs in order to augment the size of our datasets, as well as to improve the quality of our data. For example, to balance our datasets, to ultimately improve our ML research. Data privacy is one of the major roadblocks in healthcare research. In recent years, we've seen a huge increase in the amount of ML code that has been open sourced to contribute to ML research. But this becomes more complex when talking about healthcare data, which contains sensitive and private information that cannot be freely shared. Traditionally, data anonymization techniques have been used, but they do not seem as useful as real datasets for training ML models. Other alternatives, such as encryption models, could be valid, but there is a concern that they could lead to data breaches. Federated learning is an interesting alternative, although it relies on a cloud infrastructure that needs to be available in both ends. And also, input data is not usually available for researchers to interpret results. We are currently exploring how we can use GANs to generate synthetic data that is representative to the real data, but that doesn't rely on masking or omitting the real data. So we can have a strong privacy guarantee that our data won't leak any private information. Using GANs to generate synthetic private datasets could be a huge step forward in healthcare research, as it would make healthcare datasets more easily accessible, allowing us to train our models with more and more diverse data. The end goal of our research on data augmentation and data privacy using GANs is to create a synthetic data generation platform. This platform would allow a user to input a dataset of any kind and instantly obtain a dataset that is synthetic but representative of the real one. This synthetic dataset could be used to train the same ML models as the real one, but maintaining data privacy. In order to build this platform, we need to investigate GANs further and explore many different GAN architectures that can take any data type. Ultimately, this research would strongly benefit our ML research by improving the performance and generalizability of our ML models, by allowing us to augment our datasets first, as well as breaking barriers to data sharing. Thank you all for your attention. If you have any further questions or if you have anything that you would like to share with us, feel free to connect with me on LinkedIn or via email. I'd love to get in touch. Thank you.
Wow, thank you. That was amazing. And I know this virtual audience is giving you a huge virtual round of applause.
Thank
So
you.
much for sharing, Marta. That was awesome. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.